next stage that we're going to do is to run compilation. So we want to demonstrate that we're using a real functional design. So you don't think you're just working on some sort of a fake example or something. I want to show you what this really does in the world, to show you that this is something feasible and real. And so what we're going to do is we're going to take a simple C program. We're going to write a C program. We're going to compile it. Then we're going to load it onto the SoC and run it. Of course, this is not going to be loaded physically. It's going to be run in simulation, but it's going to be run on the real RTL of the entire thing that we can go and put on an FPGA or tape it out. So to run a program, what we need is a software tool chain. A software tool chain is the way to compile a program. So we're going to use the GCC compiler to compile, assemble, and link our program. And we're going to provide a set of bare metal libraries for functions like printf. So we need these libraries that can run without an operating system that we're not booting on here. So we're going to provide something like printf that's going to be really simple and can run on this SoC. We're going to provide some scripts that make files to run the compilation flow as well. Okay, in our workspace, we have a directory called apps, which we did not talk about in our previous parts of this video series. And inside the apps folder, that's where we have all of these files of the toolchain, and that's where we're going to be writing our C program for running. Okay, we have these software utilities libraries. Those are the bare metal libraries and reference folder that have scripts, libraries, link maps, and all kinds of other things that are going to be needed to be used by the software toolchain. And I'm not going into how the software toolchain works. I'm just going to show you that if we take it out of the box and run it, we're going to be able to load our C program or our compiled C program onto this SoC. So we're going to make a new folder for our program and write our C code in a file. Okay, and to compile the program, we're going to use this comp-app-local.sh program, which is under the software utilities directory. So we're going to do two dots swtils comp-app-local.sh and the name of the program, such as hello world or something like that, .c, and it's going to compile our program. So what about simulating the memories? So the memories are provided as hard macros. These are custom design blocks. They're not RTL. They're not Verilog code that we know how to simulate. They are actually something that's made with transistors and so forth, so we don't know its digital functionality just by looking at it. For simulation, we're provided with a behavioral model of this. So there is a Verilog model, a .v model, that is spit out of the compiler, and it gives a digital type of behavioral model for the memories. This is not a synthesizable model. It's not something we're going to give to our synthesizer. We're going to provide it to our simulator, and it's going to simulate it. So in the test bench RTL source list, we read in the file, the .v file of the memories. In the synthesis source list, we do not provide this guy. Instead, we provide a .lib of the memory, and the .lib of the memory tells us its timing and its power and so forth, which is going to be used by the synthesizer, such as we do for standard cells or any other type of hard macro. So we have the .v behavioral model, which is going to enable us to do simulation, and the .lib, which is going to help us do synthesis. However, we have another option here. So for simulation, we're going to preload the memories, and the problem is that when we go and take one of these big memories with whatever 16K words or 32K words, to go in and in simulation go and write something to each one of them is going to take a long simulation time. And all we want to do, we don't want to test their functionality. We just want to actually, especially because it's a behavioral model, right? We just want to load them with some sort of data. So what we can do is we can provide a Verilog task that reads the memory content from an initial state file. So we're going to provide in the simulation, in the compilation, some sort of file that says what the state of the data memory and the instruction memory should be after when we load the file. Obviously, in Silicon itself, we're going to have to go in and write each and every single one of these words into the memory, but it's going to be a lot faster when we're running at a gigahertz or whatever than doing it on a simulator that has to run probably millions of operations in order to do one of these loads. Okay, and the way we do it is we add this plus memload equals preload to the xrun command. And so we'll see that, and then it will do what we need to do, and it will load the memories with the data. So we'll have our instructions sitting in the instruction memory and the relevant data, such as variables and so forth, in the data memory. So a couple of other things I want to look at. I have this RISC-V source list. So these are basically all the files that I'm going to need for my synthesis to go and read the RTL of them. And I also have my test bench. In my test bench, I have a source list for RTL simulation, gate level simulation, and so we can see that these files are all needed for my RTL simulation. and then I have my actual test bench, which is tblp RISC-V. I also have another file called tblp RISC-V mem package, which is a thing that shows me how I can kind of cheat and preload the memory of the SoC. So what I want to do is, after I compile my program, I'm going to have a snapshot of what should be inside the instruction memory and what should start inside the data memory. And I don't want to go and wait millions of cycles while it actually loads all these things through some sort of external interface like a SPI or a UART or something. So what I'm going to do is I'm going to use a Verilog trick, which is preloading it, and it's just going to like immediately put these things inside the memory. So how do I do that? I have this this package over here that's going to take care of that, and inside my .f file, you know, the thing that I'm going to read when I go into my Xrun, I have a trick over here that says, okay, read this tblp RISC-V mem package and then do memload equals preload, which is going to go and read these pre-prepared files of all the memory snapshot. And in a second, we're going to create those guys. They're going to be actually inside this SLM files directory under TB. So right now that is empty, but we're going to populate it in one moment. So the next part that I want to show you is how we actually write a C program and compile it. And we had this apps directory, which is where I'm going to have my whole tool chain for preparing files for the SoC and compiling them and so forth. And we've given you here 4 directories, where these 3 directories are the tool chain itself. So they're libraries and some other reference files and some utilities for compilation. These were provided by the tool chain, mainly prepared by the pulp guys, and they provide us a way to use GCC to prepare all the files we need in order to boot up this this core and use it and so forth. Specifically inside software utils, there is a program called comp app local, a script, which is like a make file that's going to use the RISC-V pulp tool chain to compile using GCC. Okay, so that said, I'll show you how to do it. The other thing we have is this bubble sort, which is a program that I prepared. So you can prepare your own program, make a different folder and write a C file. So bsort.c is just a simple bubble sort. Okay, what it's going to do basically, it's going to go and it's going to take an array of numbers, including something that we added, which is my ID over here, and it's going to sort them in order, and it's going to and then our test bench, which I opened quickly before, and I'll show you now, what it's going to do, it's going to actually go through and it's going to print out the unsorted and then the sorted files. So let's go over to the test bench over here. So what the test bench is going to do, it's going to connect everything together, and then it's going to go and preload. As I showed you before, it's going to preload the memory. So it's going to take all of those files that we're going to compile right now and make a snapshot of them and put them inside the memory. And then it's going to go and it's going to run through the array that currently is there with all kinds of random numbers, and it's going to print out the address of the memory array over there and what its content is. Then it's going to run for a while until the done flag goes up, which means that the program finished running as it was reading through the C code, and then it's going to again go over and print out the values of the vector, and we should see that they are sorted. So first thing we're going to do now is to compile this thing. So right now we're under our workspace directory, so I'm just going to change directories into the apps and then bubble sort directory. And what I'm going to do is I'm going to use that under software utils, that comp app local, and my program is called bsort, so I'm going to write bsort over here, and that is going to compile my program. And when I compiled my program, we can see here now that I have all kinds of files, not just bsort.c inside here, but I have all these other files which are, again, what we should load into the different parts of the SoC, including the instruction and data memory and so forth, in order to run the program. So these are the compiled programs. And also we copied over the important ones into the SLM files directory over here. So in the SLM file directory, we see addresses and their content of what we're supposed to load onto the SoC, and this will be done by this, again, this special preloading the memory command. Okay, so that was created by our compilation. So now that we have compiled our program, we can actually go and run a simulation. So I'm going to go back over here, and I'm going to go back to my workspace. And now what I can do is I can just run xrun with the regular simulation kind of command. So I'm going to go to scripts, right, and look at my xrun options RTL. My xrun options RTL is going to have the -f to that TB RISC-V RTL source list, which we looked at before. That's what it's going to go into. And we also asked for, I prepared a little simulation script that would put our GUI onto the screen at the end. So let's run that. Xrun -f scripts xrun options RTL. Okay, that's going to run pretty quickly. It runs nicely. It's not a very large design. Okay, and it already printed out the first part, which is the pre-sorted vector before it ran the simulation. Okay, and now we can go and we see that something was done over here. We can actually look towards here at the end, and we'll see that right at the end of the simulation, the done flag went up, and the done flag went up actually caused the entire simulation to finish. And we can see that different things throughout the simulation were running on these instruction memory and data memory buses. Okay, but maybe the important thing that we want to see here is that this worked. So here is the log, and we see the pre-sorted vector this was our ID that we put in. That was the number we put in was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, and it is, as you see, the vector is unsorted right now. And now we ran bubble sort, and what we see is that this number came out first, ours came out second, and the rest are all sorted. So our bubble sort really worked, and this was all done on a real processor, written in RTL, and run with a logic simulation. So I think that I just wanted to show you over here what the components of our design are, prove to you that this is a real design that actually can do things. You can go and write C programs and so forth and work with it, and that's like our starting point for going into the physical implementation of this design.